acid isn't super pure, so before getting started, I decided to clean it up a little. I dumped it all into a beaker, and then I added a whole bunch of distilled water. Although adipic acid isn't very soluble in water, we still don't want to add too much here. Before continuing, I quickly checked the pH, which came out to be around 3, which is expected for adipic acid. I made a solution of about 6 molar sodium hydroxide, and I started to add it slowly. The sodium hydroxide is a strong base, and it will quickly react with the adipic acid to form sodium adipate and water. Unlike adipic acid, sodium adipate is very soluble in water, so as we continue to add the sodium hydroxide, the solution should clear up. I know I'm done adding sodium hydroxide when I get a pH of around 7. All of the adipic acid should be in the form of sodium adipate, and the cloudiness here is due to impurities. The impurities that are present seem to be very small particles, which tend to easily pass through filter paper. So to get rid of them, I have to instead filter it through something called sea light, which is very similar to extremely fine sand. The solution passes through relatively slowly, but the stuff that I collect is crystal clear. Once everything is relatively similar to them, I have to instead filter it through something called sea light, which is very similar to extremely fine sand. The solution passes through relatively slowly, but the stuff that I collect is crystal clear. Once everything has been filtered, I wash the beaker and the funnel with a little bit of distilled water. I again wait for all of this to pass through, then I take away the funnel and I drop in a stir bar. So now that I've cleaned things up a little bit, it's time to regenerate the adipic acid. To do this, I add 6 molar hydrochloric acid until I get to a pH of around 1. The hydrochloric acid reacts with sodium adipate to make adipic acid and sodium chloride. The sodium chloride is very soluble in water, but the adipic acid isn't, so it precipitates out. I continue adding the hydrochloric acid until I get to a pH of about 1. The beaker is placed in a freezer and cooled to around 5°C, and then the adipic acid is filtered off. The beaker is washed a few times with a small amount of distilled water. Once everything was pulled through, I turned off the vacuum and did one final and thorough washing. I turned the vacuum back on and I left it running for about 20 minutes to try to dry it up as much as possible.
Agilent, atomic absorption solutions. Need a versatile solution for elemental analysis? Agilent flame and graphite furnace atomic absorption solutions match any analytical need and budget, allowing quick and easy measurement of up to 60 elements. In a variety of industrial samples, environmental, food, materials, pharmaceutical, academia, energy, and chemical.
I scraped the adipic acid out of the filter and I let it dry for 2 days. When I came back, it was a relatively dry powder, and I transferred it back to the original container. Okay, so now we're ready to do the actual reaction, and I start by dropping in a magnetic stir bar. I then add 5 grams of adipic acid, followed by 70 milliliters of dichloromethane. And the last ingredient is a small amount of dimethylformamide, which will be acting as a catalyst. I took away the funnel and I replaced it with a vacuum adapter. Above the adapter, I attached a small addition funnel and I added 11.6 milliliters of oxalochloride. Oxalochloride is a very dangerous and corrosive liquid, and you can see it fuming. It's a very strong chlorinating agent, and I do my best to avoid working with it. To the vacuum adapter, I attach some tubing which leads outside. This reaction produces a lot of hydrochloric acid gas as well as carbon monoxide, so this definitely cannot be done in a closed space. My workspace is extremely well ventilated, and I just added this tubing as an extra precaution. When I was ready to get things started, I turned on the magnetic stirring. Most of the adipic acid is not going to dissolve, and this is perfectly fine. I open the addition funnel, and the oxalochloride is added over the course of about 5 minutes. My dichloromethane and adipic acid aren't perfectly dry, so there's a little bit of water present. The first little bit of oxalochloride that's added is going to react with the water, and it can sometimes be pretty vigorous. It's highly unlikely that it would ever cause it to bubble out of the flask, but it's just a good precaution to take. Anyway, so as I said, the initial reaction is just with water, which produces hydrochloric acid gas, carbon monoxide, and carbon dioxide. Once it reacts with most of the water and gets rid of it, it will start to do what we actually want it to do, which is react with the adipic acid. When it does, it will convert the carboxylic acid groups to acyl chlorides and lead to the formation of adipoyl chloride. It will also produce carbon dioxide, carbon monoxide, and hydrochloric acid gas as side products. This is why it's really important to have good ventilation, because you really don't want to be breathing in hydrochloric acid or carbon monoxide. Because oxalochloride is breathing in hydrochloric acid or carbon monoxide. Because oxalochloride reacts with water, and I want to make sure that all of the adipic acid is consumed, I need to use an excess of it. I used about twice the amount that was required, which assures that the reaction will go to completion, but it also means that oxalochloride will be left over at the end. I'm now just going to quickly go over the mechanism. In the first step, the electrons on the nitrogen of DMF move to form a double bond. The other double bond opens up, and the electrons go to the oxygen. The free electrons of the oxygen then attack the carbonyl of oxalochloride and open up the double bond. The electrons on the oxygen then move to reform the carbonyl, and the chloride is kicked off. The free chloride then swings back around and attacks the double bond. This leads to a cascade of electrons jumping around and the formation of the active Vilsmeier reagent. The carbon bonds in the oxalochloride are broken apart, and it leads to the formation of carbon monoxide, carbon dioxide, and another chloride ion. The chloride then attacks adipic acid and pulls off an acidic hydrogen. The electrons shift and the carbonyl is opened up. The free electrons on the oxygen then attack the Vilsmeier reagent and kick off a chloride. The chloride ion that's kicked off will then attack the carbonyl. A carbon-oxygen bond is broken, which regenerates our DMF catalyst and forms the final acid chloride product. The reaction is then flipped. The free electrons on the oxygen then attack the Vilsmeier reagent and kick off a chloride. The chloride ion that's kicked off will then attack the carbonyl. A carbon-oxygen bond is broken, which regenerates our DMF catalyst and forms the final acid chloride product. The reaction is then repeated to the other side of adipic acid.
Hey video creators, with Envato Elements you can create better videos. How? With unlimited downloads of millions of creative assets, all
After the last bit of oxalochloride was added, it took about 3 hours for the adipic acid to completely disappear. During this period, the bubbling slowed down a lot, and the solution slowly became more and more yellow. Adipoyl chloride is slightly yellow, so this color change is a good sign. Eventually, all of the adipic acid was consumed, and there was no visible bubbling. From this point, the solution was stirred for another 24 hours. 24 hours later, the solution is significantly more yellow. It's also opaque due to impurities, which will need to be filtered off. To do this, I filter it through some sea light and glass wool. Before filtering through the actual solution, I wet the sea light and the glass wool with a little bit of DCM. It's important to use glass wool and not just regular cotton, because the oxalochloride and the adipoyl chloride would probably destroy it. I tossed away the solvent that passed through, and then I started filtering the real thing. One thing to be aware of is that adipoyl chloride is sensitive to water, so it will react with moisture in the air. In theory, it's best to do this in a water-free environment, but I don't have one, so I tried to just filter it as fast as I could. One thing that's helpful is that we have excess oxalochloride left over. Oxalochloride is much more reactive, so in theory, it should be able to pick up the water and protect the adipoyl chloride. Once everything had passed through, a small amount of dichloromethane was used to wash the round bottom, as well as the funnel. When this was done, I took away the funnel and I dropped in a stir bar. Okay, now I need to get rid of all of the dichloromethane, as well as any unreacted oxalochloride. And to do this, I set up a simple vacuum distillation. I set up a hot water bath, and with strong stirring, I slowly turn on the vacuum. It's really important to engage the vacuum slowly, otherwise it could bubble out of control. I continue with the distillation, and unfortunately, at some point it becomes opaque again. This isn't a huge deal, but it does mean that I have to do another filtration. Anyway, I keep going until it completely stops bubbling, and I'm left with this dark orange residue. In a previous run that I did, it didn't turn orange, and I just had a yellow liquid. I'm not exactly sure why there was such a difference here. In either case, though, I had a mixture of adipoyl chloride and a bunch of solid impurity. Unfortunately, most of the impurity comes from the dirty adipic acid that I started with. If I started with very pure adipic acid, I probably would have had relatively clean adipoyl chloride at this point. Anyway, it is what it is, and I now need to separate my adipoyl chloride from the other solid junk. To do this, I start by adding 50 grams of dry cyclohexane. The cyclohexane will dissolve the adipoyl chloride, but it won't dissolve the other stuff. After it's added, I put the stopper back in, and I stir it for about 10 minutes. To filter it off, I do the exact same thing as before, where I pass it through sea light and glass wool. Before I pour it in, I wet things with about 2 grams of cyclohexane. Anyway, the cyclohexane solution is added to the funnel, and it slowly starts to filter through. At this point, we can see that the solution itself is yellow, and the orange color is coming from the solid stuff. I added as much as I could without including the solids to try to get it to filter through as fast as possible. Once Once almost everything had filtered through, I poured in the last bit that remained. The flask in the funnel was then washed twice, first with 10 grams of cyclohexane, and then with 16 grams. In total, I used 78 grams of cyclohexane, which is almost exactly 100 milliliters. I wait for everything to pass through, and when it stops dripping, I take away the funnels and I cap the bottle. What I have now is roughly a 0.2 molar adipoyl chloride solution, which will be used directly to make the nylon. The solution is a little bit opaque because some of the adipoyl chloride reacted with water in the air and precipitated adipic acid. To make the nylon, I need to make a solution of hexamethylene diamine. When I open the bottle and take a look inside, it's completely solidified and it has formed some very nice crystals. With a lot of difficulty, I scraped out 4.4 grams and added it to a beaker. Hexamethylene diamine is quite corrosive, so it's important to wear gloves and be careful when handling it. I added 50 milliliters of distilled water and I stirred it until everything dissolved. Some of the flakes floated to the top and started to zoom around, which I thought was pretty interesting. Anyway, once almost everything had dissolved, I topped it off to about 100 milliliters. With the hexamethylene diamine solution prepared, I'm ready to make the nylon. The adipoyl chloride seems to have gotten a little bit cloudier, but that's not really an issue. To make the nylon, it's pretty simple. I first add a little bit of hexamethylene diamine solution, and on top of this, I carefully add an equal amount of adipoyl chloride. The adipoyl chloride is dissolved in cyclohexanol, which doesn't mix with water, and it's less dense, so it floats on top. Because they're not mixed, the only place that polymerization can take place is at the interface between the two solvents. Using a pair of tweezers, I can pinch the nylon and pull it out of the beaker. The gooey string is wrapped around a glass stir rod, which I can then turn to pull out more nylon. What's interesting here is that the nylon I'm pulling out is not actually a string, it's more like a tube. The tube isn't hollow though, and it's often filled with hexamethylene diamine solution, so it's important to be careful when handling it. So now to talk a little bit about what's going on here. When the adipoyl chloride comes in contact with the hexamethylene diamine, it reacts to form an amide bond. However, on one end of this newly formed molecule, we have an acyl chloride, and on the other, we still have a free amine. So now the reaction can repeat itself, and it keeps doing this over and over to form a very large molecule known as a polymer. It looks like there's a whole bunch of nylon here, but it's a little bit deceiving because it's being puffed up a lot by the water that's being pulled up with it. It eventually runs out of either the hexamethylene diamine or the adipoyl chloride. When I squish it with my fingers, you can see that there's a lot of liquid with the nylon. To try to clean it, I dump it all into a water bath. Without destroying the nylon, I manually pull it apart to try to give it a better washing. After about 30 seconds, I just leave it there to soak, and I move on to making more nylon. I tried it again using the same amount of each ingredient, but this time in a much larger beaker. It ended up being pretty much the same thing, and the only difference was that it was a little bit faster. There's a larger surface area between the two layers, so we pull more nylon with each turn. It was a little bit tedious doing all this turning, so I tried to make things a little bit more automated. A glass stir rod was taped to an electric drill, so this time I just need to click a button to pull out the nylon. For this run, I decided to see what would happen if I just mixed the two layers together instead of pulling the nylon out. As I continue to stir, it slowly forms the nylon and turns into a somewhat disgusting mess. After about a minute of stirring, I'm left with an alien-like blob stuck to the end. When we take a closer look, we can see a whole bunch of air as well as liquid trapped inside. I then attempted to get creative by adding some fluorescein to the hexamethylene diamine. Fluorescein is a highly fluorescent molecule, especially under UV light. I actually made it in a previous video, and if you're interested in checking that out, there's a link in the description.
Hi, I'm Jen Tonic, and I'm a tattoo artist specialized on botanical and naturalist designs. I work at the Sticks and Stones studio in Berlin, and I have the honor to be sponsored by amazing brands like Cheyenne Tattoo Equipment, Eternal Ink, and Balm Tattoo. When designing tattoos, I'm mainly inspired by everything from nature. Tattooing flowers and plants gives me the possibility to fully express how I see the world. It also allows me to help others feel comfortable in their own skin by decorating it with unique art pieces. Our body is our permanent home, so why not decorate the walls and put some art on our skin? In this Domestika course, you will learn how to design botanical tattoos in full color, following the natural body anatomy and flow. As your final project, you will design a unique tattoo inspired by nature using Procreate. First, we will go over some important aspects you should consider before getting a tattoo or drawing one for a client. You will see the importance of getting the right picture, collecting references for inspirations, and choosing the right color palettes. Next, you will learn about flower anatomy and how to pick the best ones for your design. We will study our body and see how its flow can affect our chest piece design. Then it's time to sketch some ideas that will help us define our final project and balance our lines to make the tattoo age well. With our outlines done, we will see how color can be used to match different skin tones. Before wrapping up, we will learn how to apply the stencil onto the skin, correct its size, and make your design stand out by using depth. Finally, I will share some valuable tips on getting the tattoo done, taking care of it, and using your design in other ways. By the end of this course, you will be ready to design beautiful tattoos that show off your personality. To follow my steps, you will need basic drawing skills, Procreate, or other tools of your choice. Learn how to embrace each body through botanical tattoos.
I turn off the lights and I turn on my UV light, and then I carefully add the adipoyl chloride. Just like before, I use the tweezers to pull out some nylon. What's kind of cool is that we can tell how much water we're pulling up with the nylon based on how bright it fluoresces. At some point, I accidentally got the nylon stuck to the side of the beaker. At first it was a mistake, but it ended up being pretty interesting. In hindsight, I wish I put down the glass rod, and using my fingers, I probably could have pulled off a super thin sheet of nylon. In another run, I just poured in the adipoyl chloride and then did absolutely nothing. I left it for about an hour, and I wanted to see what would happen if I just let it react passively. When I came back, the adipoyl chloride layer was no longer yellow. I poked around with a glass stir rod and tried to pull some nylon using tweezers, but it appeared that everything had reacted. What's interesting is the same amount of nylon has formed here as all of the other runs. In the other runs, when I pull it out using tweezers, it's an extremely thin layer, and it makes it look like I'm pulling out a whole bunch of nylon. However, in reality, there's actually only a very small amount. For the last run, I used a lot more of each, and I thought it would take a while, so I used the drill as well. Near the end, it got super messy and was pretty gross looking. I ended up having to transfer the huge messy blob and restart with a fresh glass rod. The nylon from all of the runs was combined in the same bowl and given a thorough washing. Mixed with the nylon is a lot of unreacted adipoyl chloride, hexamethylene diamine, and also the fluorescein that I added in. After a thorough washing and having to change the water several times, I'm left with relatively clean looking nylon. I personally didn't do it, but to clean things further, it might be an idea to do a dilute acid and a dilute base wash. Anyway, the nylon